Hello everyone. In this session, we will discuss how MOSFET acts as a switch. MOSFET as a switch. So we already discussed the MOSFET characteristics. MOSFET is two types, D MOSFET and E MOSFET. In that linear region, it will act as a switch. But in this session, we will discuss some of the characteristics during the MOSFET as a switch. So in that, generally, load driving applications like LEDs, load driving applications like LEDs, light emitting diodes. LEDs means light emitting diodes. They required only less amount of current, that is microamps and the milliamps. BJT is the cost effective. Whenever the current requirement in microamps and milliamps, the example is LED, that is BJT is very cost effective. BJT is very less cost. In case of load current is in amperes, for example, load current in amperes, microcontrollers logic switching applications, MOSFET is preferable. Okay, if the load current is in amperes and we have microcontroller logic switching applications, in the microcontrollers used as a logic switch applications, that MOSFET is preferred. Okay, this is the main difference between the BJT and the MOSFET. Understand? Right. In continuous switching, high frequency switching also MOSFET preference. The switching is very continuous and high frequency switching. Frequency also very high. Frequency also very high. In that cases also MOSFET is the very preferable, very interesting. Okay, but BJT is not preferable in this region. Third, when it is on low conduction loss. When it is on means here when MOSFET is in on, it has the low conduction losses. So this is the MOSFET, this is enhancement MOSFET. When it is on, for example, this having current is 10 milliamps and the resistance between the drain and source is nothing but the RDS. Whenever it is on, it has the resistance 0.01 ohms. 0.01 ohms. Then the power equal to I square R. Then the power equal to I square R. Power equal 10 square and the loss is the 0.01. Then the power equal 1 watt. 1 watt is this is the switching loss. This value is nothing but the switching loss. So this amount of loss will be occurred on the MOSFET. Okay. Yes. In this case, RDS on means what is this meaning? Resistance between drain and source. When MOSFET as on switch. When MOSFET as the on switch. Okay. Right. Next, when BJT and MOSFETs are used as switches, there are two types of losses. We have the two types of losses. First loss is the conduction loss. Second loss is the switching loss. Whenever it conducting, it has some loss, that is the conduction loss. When switching happens, switching means it may be on to off or off to on. The loss will be possible. That loss is called the switching loss. So it for both for BJT as well as the MOSFET. Here MOSFET is more thermally stable compared with the BJT. When we are discussing the characteristics, already we discussed this point that MOSFET is thermally stable compared with the BJT. You know that it will adapt the more temperature compared with the BJT. Here MOSFET, it is positive temperature coefficient. MOSFET is the positive temperature coefficient. How you will say this positive temperature coefficient? As when temperature increases, the on resistance will be increases. Whenever on resistance will be increases, the drain current will be decreases. Whenever the drain current will be decreases, automatically temperature will be decrease. How? This temperature is nothing but the heat. Heat means ID square into R on. So this value decreases. This value decreases, heat value is decreases. So when first initially temperature increases, due to this process finally the temperature will be decreases. This is the positive temperature coefficient. Positive temperature coefficient means the increment in temperature itself decrease in the temperature by this process is called the positive temperature coefficient. Here BJT has the negative temperature coefficient. Then what happened? Look at here. Negative temperature coefficient means the temperature is negatively increases. Temperature is increases itself, as when temperature increases the collector current will be increases, and whenever the collector current increases automatically the temperature again increases. If heat is not dissipated, generally heat must be dissipated. If this heat is not dissipated, then BJT becomes into the thermal runaway. BJT becomes into the thermal runaway. That is the problem with the BJT. That is the problem with the BJT. So that's why whenever MOSFET is thermal is positive temperature coefficient and BJT has the negative temperature coefficient. Understand? Right. Next. Here we have two types of MOSFETs. One is D MOSFET and another one is E MOSFET. D MOSFET and the E MOSFET. Here in these two things, E MOSFET preferred than the D MOSFET as a switch. So why? The reason, we have to discuss the reason. Do you look at here? To make off switch for the D MOSFET, VGS must be negative. So we should apply some biasing here. Off switch means to become current zero, we should apply the negative. Because initially VGS is 0, by applying a negative voltage at a particular negative voltage, the current from drain to source is 0. So that's why we should apply the negative voltage here. Second, but in case of this is the D MOSFET. To make off switch for the E MOSFET, if it is E MOSFET, we no need to apply any biasing. Normally, it is generally D MOSFET means normally on switch. Normally a on switch. But here VGS is 0 means normally off switch. So no need of biasing. Here there is no need of biasing. Here biasing is required, but here the no need of the biasing. Here VGS is the 0. Right. So that's why to make it as an off switch, we should again apply the bias, but here to make it as an off switch, there is no need to applying the bias. That's why it is normally on switch, this is normally off switch. To make on switch for E MOSFET, VGS is greater than VT. So in order to make it on, always we should give the input voltage more than this threshold voltage. More than this threshold voltage. Whenever the input voltage is more than the threshold voltage, it will be on. So for that purpose we should apply the biasing. So here generally whenever it is in on switch, the resistance between the drain and source RDS equal VDS by ID. That means the voltage between drain and source and the drain current. Generally this is linear or ohmic region. This is generally linear or ohmic region. This region is called as the linear region or the ohmic region. You know that when we are discussing the characteristics of the MOSFET, it will give the RDS value. Here, when VGS is increases, RDS decreases. If you go for still increasing the VGS, then RDS value on will decreases. RDS is very important factor here. RDS is the very important factor here. That RDS, the resistance between the drain and source, will be deciding factor how to act as a switch of MOSFET. Okay, next. So in order to use the MOSFET as a switch, we need to arrange some manner. Here for the gate terminal you should connect a control circuit. That control circuit will operate the gate. This control circuit will operate the gate. then it will act as a switch. For example, by controlling circuit, if the VGS should be 0, VGS should be 0, there is a drain current is 0, there is no current for the load. If VGS is more than threshold voltage, by using this control circuit, by applying the voltage, automatically it acts as a on switch, then the drain current will flows into the load. That's why the control circuit is here very important role. It has the very important role here. Okay, yes. Next, in order to operate MOSFET in the linear region, properly select VDD and ID values. We should select the properly VDD and ID values. How we should select VDD and ID values? Generally, so we should discuss some points here. When MOSFET is on, when the MOSFET is on, for example, MOSFET is on condition. MOSFET is on means what is the problem? The voltage between the drain and source is the 0. I will write VDS value is the 0. Then what is the drain current? How will write the drain current? Drain current is like this. Drain has some resistance, so I will write like this. So generally drain output equation is like this: VDD minus IDRD minus VDS is equals to 0. When VDS is 0, substitute this VDS in the 0, then you have VDD equal to IDRD equal to 0. From this we will find out the drain current ID equal to VDD by RD. VDD by RD. So can I write? I will locate this point. This point equal to VDD by RD. VDD by RD. So in this, when MOSFET as off switch, then what happen? The drain current is 0. There is no current for the drain current. In this we will write VDD minus VDS equal to 0. From this we can write VDS equal to VDD. VDS equal to VDD. So can we write this? VDS equal to, this value is the VDD. Then combine together. Then you should combine together. So take it, this is the VD value. This is the VD value. So this is the load line. We can take it as this is the load line. In order to operate as a switch, you should operate in this load line. In order to operate as MOSFET as a switch, you should operate in this load line. Then it will operate very effectively. Then it will operate effectively as a switch. So here, in order to operate as a switch, gate should be connected to the control circuit, but gate must and should have some resistance. That resistance is RG. That resistance is RG. That is the gate resistance. What is the gate resistance? What is the use of the gate resistance? This gate resistance RG protect the control circuit. It will protect the control circuit. It will protect the control circuit. If there is no RG, what happen? MOSFET is draws lot of charging current. It will draw the lot of charging current. The problem is if RG is not available, MOSFET draws lot of charging current. So that's why here always you should maintain the, for always you should maintain the gate resistance for the control circuit. If there is no RG means it will draw the MOSFET will draw the lot of charging current. In order to avoid the charging current, you should maintain this RG. And with RG also you should maintain some resistance. This resistance is called as the pull down resistance. What is the use of the pull down resistance? It should be required. This is also required at the gate terminal. So the importance is when input is 0, if there is no input, when input is 0, MOSFET remains in the off condition. In order to maintain MOSFET remains in off condition, this pull down resistor is the applicable. Its pull down resistor is the applicable. So in order to operate a MOSFET as a switch, you require two resistance. One is the gate resistance, another one is the pull down resistor. This resistor is the pull down resistor. This pull down resistor is when input is 0, in order to maintain the MOSFET in the off condition. In order to maintain the MOSFET in the off condition. That's why in order to operate as a switch, control circuit consisting of the one resistor, gate resistor, and another one is the pull down resistor. Another one is the pull down resistor. Next, so whenever MOSFET is acting as a switch, we should discuss about the drain voltage as well as loss across the MOSFET also. So whenever this is the drain voltage, this diagram is the drain voltage. So this drain voltage, this waveform shows the drain voltage waveform, and this waveform shows the output current. Output is nothing but here the drain current. So look at here, this drain voltage, initially the drain voltage is less and not switching here. Maybe this point is the on switch, this point is the on switch, for example. If the MOSFET is in off, the MOSFET is in off, and we are on at this point, it will, the current will be slowly increases, and at a particular point, whenever it is on, MOSFET is on, then the voltage in the MOSFET will be decreases, and current in the MOSFET will be increases. So decreases and it will maintain the low voltage, and current will increases and it will maintain the high value. So after completion of the switching, whenever the switch is off, then automatically switch is off, the drain voltage increases, that means output voltage is increases, and output current will be decreases. So whenever this process is happening, why it is happening? Because MOSFET is have some switching losses. It has some switching losses. So due to the time delay, drain voltages have time delay, and the drain current has some time delay. Due to these time delays, what happened means, look at here, between this VD and ID, the loss will be slowly increases to this point. After that, the voltage will be decreases, current value low value, and it will be decreases. And so the combination of this voltage and current, we have some loss, because in off switch also drain has some leakage voltage, so the drain voltage and drain current, it has some loss of power, and after that, whenever the switch is off, then automatically this will be increases and the decreases. At this point, this zone is the switching zone. Generally this zone is the switching zone, so that's why this is called the switching loss. This zone also the switching zone, that's why it is called the switching loss. It is called as the switching loss. Okay, and this zone is This is a switching zone, that's why we have the switching loss. In these regions, so this region, this point to this point, it will be on. On means this region is called the conduction loss. This region is called the conduction loss. This region is called the conduction loss. Okay, so that's why whenever MOSFET is acting as a switch, it has two types of losses. One is the switching loss during the switching time, that means it may be on time, it may be off time. And the second loss is the conduction loss. Whenever MOSFET is the on, automatically conduction loss is possible. Okay, so this is how the MOSFET is acting as a switch and the different characteristics. Okay, so in this you should remind the each and everything, and it will be very useful for you. Here the switching losses are the important losses. Okay, I hope all of you understand the session. Thank you.